You're sleeping right in your bed, and all of a sudden, you hear a sound. That's a mosquito. Is it coming towards or is it going away? Obviously, from the frequency of sound that you hear from the mosquito, you can tell whether the mosquito is flying towards you or is flying away. If it's flying away, it will be away it goes. Good day, it's your man Chips. We're moving on today to Doppler effect for sounds, e.g. of sirens, mosquitoes, and hooters. But what is Doppler effect? Doppler effect is the change in frequency or pitch of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of the sound propagation. Another way of putting this across is to say Doppler effect is an apparent or change in observed or detected frequency, which is the same as pitch, as a result of the relative motion between a source and an observer. All right, now there are a few words that we can think about here. One of the words that we can talk about is frequency. Frequency is the amount of hits per second. In other words, it's the amount of times that a wave gets to a place per second. I'm sure from previous grades, you picked up that frequency is equal to, do you remember? 1 over t, okay? Where t is the period, all right? And we also know an equation that's common that says velocity is equal to f lambda. I'll talk about this a little bit further. But very important is to realize that frequency is the same as pitch. I like this definition because in an exam it's a very short definition, a change in observed or detected frequency as a result of the relative motion between source and observer. So between a source and an observer, there is a change in frequency. The frequency can be increasing or the frequency can be decreasing. Right? That's something to think about. Here is a picture form of what I'm talking about quickly. Look at it. Try to understand what's going on here. If you look at the picture that's up on the board, you can agree with me that when you have got the observer and the listener both stationary, in other words, velocity being equal to 0, the frequency heard by listener is the same. In other words, it's not increasing, it's not decreasing, it's a constant. So this is when source is at rest and listener is at rest. However, if the source begins to move, let's say this is a police car, it's moving away from listener, okay, producing a sound. What's going to happen? The frequency of that sound produced is going to become less. But what does this part represent from here to there? What do those lengths represent? Those lengths represent lambda, which is the wavelength, which is the distance between any 2 points that are in phase. All right. What do we see about the wavelength when now we have got the source moving away? The wavelength increases. How about the frequency? The frequency decreases. Why? Because wavelength is inversely proportional. This comes from the fact that wavelength is inversely proportional to frequency. When we have got a constant velocity, we introduce the constant. That's where we would say then F is equal to V over lambda. Okay, in other words, velocity is equal to F times lambda. These are quite important parts of our study. So what's happening to the frequency here? The frequency is increasing. What's happening to the wavelength? The wavelength is decreasing. Why? Because now we have got the source of sound towards listener. Air is being compressed, okay? And so, sound waves moves through air. If the air is compressed, all right, the distance between each point in phase, which is wavelength, begins to decrease, and therefore frequency is on the increase. If you've understood this, you've understood the most of what we know. We need to know about Doppler effect. If the source of the receiver and the receiver are both stationary, then the frequency will remain the same. I think I said that. However, if either the source S or the receiver R are moving, then the frequency and the receiver and compared to the source will be different. There will be an apparent change, in which case we know that there is a low pitch or a low frequency when there is moving, the source is moving away from a stationary listener, and a high pitch when the source is moving towards the listener. All right. Now, Doppler equation is F is equal to V plus or minus VL, right? All over V plus or minus VS multiplied by Fs. Now, what do these represent? What are those values representing? Your FL is frequency observed by listener. Your V is velocity of sound. You'll be given the velocity of sound in a question. Okay? The VL is velocity of listener. The V, again, is the same as that. Velocity of source, and velocity is measured in meters per second. All right, the frequency, as we all know by now, frequency is measured in hertz. This is the frequency of the source. But how do you know when to use positive or negative? Let's go back to the diagram here. In the diagram here, we know that frequency heard by listener is equal to frequency from source. Why is it equal? It is equal merely because if you go back, they are all zero here, nothing is moving, all right? So V over V multiplied by Fs, that cancels, and it's equal to Fs. But how about in a situation where we now have the source moving away from the listener? What is the frequency observed by listener? The frequency observed by listener is going to be obviously lower. So we need a smaller number on the top. All right? So it will be V minus, okay, at the top, VL over V, a bigger number at the top, plus Vs multiplied by Vs. Okay. On the other side, right here, where we've got now the source moving towards the listener, you can agree with me, it will be FL is equal to frequency observed by the listener equal to velocity of sound minus velocity, plus. Now we need a bigger number at the top of listener all over a smaller number at the bottom, Vs multiplied by Fs. So that's where the plus or minus comes from. Before you answer a question, you must realize whether you're going to add or you're going to subtract at the top and at the bottom. But I'm sure that gives us an understanding of what's happening in this particular situation. All right, from our question papers, we would find related equations to Doppler effect. The first one, which we spoke about earlier on, and we know from the previous grades, V is equal to F lambda, and the second one, t, is equal to 1 over f, which is the same as f is equal to 1 over t. The permutations of this one we can also find using the triangle method, which I gave you the other time, that says v up at the top, f, and lambda here, okay? Lambda is the wavelength in meters, v is the velocity in meters per second, and frequency, it's in hertz, hz. All right, now this one I have explained already, which is the equation according to Doppler effect, and energy equal to hf, I'll talk about a little bit later on. But I think I can also add that if you don't have the value of f, you know that f is equal to v over lambda, okay? V, which is the velocity, over lambda. Here we got the speed c, all right, of light over lambda substituted there. We'll talk about this when we look at photoelectric effect in the next lesson. All right, let's move on. Applications of Doppler effects. The Doppler effect can be observed in waves, including ultrasound, light, and radio waves. In sonography, okay, we use ultrasound, and ultrasound is a wave whose frequency is less than, it's above 20 kilohertz, okay? You cannot hear it, but it's a wavelength that's very, very high, okay? So we use ultrasound and Doppler effect to determine the direction and the blood flow. Light is emitted by stars, okay? That's the other application of Doppler effect. Due to the Doppler effect, the frequency of this light decreases and the stars appear to be shifting in the redder direction than if they were stationary. This is called a red shift and means that the stars are moving away from the Earth. In other words, we can conclude that the universe is expanding. Here's an ultrasound application where we can find the blood rate. You got a source, okay, a transmitter of light goes to the blood, and we can measure the difference between the frequencies of the sound sent in to the small particles of blood within the blood vessel, and as it reflects upwards, we can detect the blood flow rate. Okay, this is used in sonography, sonar, generally known as sonar, okay, but we know it as sonography, as well as measuring blood rate in unborn fetuses, or heart rate in unborn fetuses. Okay, all right, so that's application there. But before we go any further, we want to look at some exam questions that we can find that are to do with Doppler effect. Okay, so here is a question that says the siren of a stationary police car emits a sound wave of 0.55 meters. With its siren on, the police car now approaches a stationary listener at constant velocity on a straight road. Assume that the speed of the sound in air is 345 meters per second. So speed of the sound in air is the value of v in this instance. Will the wavelength of the sound waves observed by the listener be greater than, smaller than, or equal to 0.55? So that's something for you to think about here. 0.55 meters here is representing the wavelength. What do we know? We know that the police car is approaching a stationary listener. You can go back to the diagram, look at the stationary listener being approached. What's happening to the wavelength? Is the wavelength increasing or decreasing? Okay, think about it. Do you have an answer? Absolutely. It is going to be smaller than. Okay, it is going to be smaller than. Name the phenomenon that you have observed at this instance. So the phenomenon that is observed at this instance is obviously Doppler effect. Okay, that is the observed phenomenon. All right, next part then says calculate the frequency of the sound wave observed by the listener if the car approaches him at 120 kilometers per hour. All right, what are we given here? All right, in this instance, we are given the speed of sound in air. We are also given the wavelength of 0.55 meters. So for us to calculate using Doppler effect, we know we need to have the frequency of the sound. All right, so that's the frequency of the source. So let's calculate the frequency of the source in this instance. So that's 6,2. How do we calculate frequency? Go back to your triangle. Frequency is equal to V over lambda. Okay? So what is the value of our V? Our V is equal to 345. We are already given it, divided by 55. And V, if it's divided by 0.55, sorry, okay, that will give us the value of the frequency. This is the frequency of source. So our frequency of source is a value of 627,27 hertz. Okay. But that's not the end of it. The question is asking us to calculate the frequency observed by the listener. Look, we are given in this instance that, right, the speed it approaches is at 120 kilometers per hour. Okay? Now, how do we convert 120 kilometers per hour to meters per second? Remember, what we are saying is there is an approaching situation, so we are going to use frequency observed by listener is equal to V plus VL over V minus Vs multiplied by Fs. If that's a situation where we got them approaching each other, okay? So our velocities are supposed to be in meters per second, but now the velocity is given in kilometers per hour. To convert kilometers per hour to meters per second, we are going to divide 120 by 3,6. You must know that from your mathematics. That should be a simple calculation where we are getting now 345 at the top because it's stationary over 345 minus 120 divided by 3,6 is 33,33 to 2 decimal places. Okay? And multiplied by the frequency of the source, which we have calculated already as 627,27. Our final answer there is going to be 694,35 hertz. 634,35 hertz. Okay, so there it is. Let's try to make sense of this. Is the frequency higher than the frequency from source? Yes, it is higher. Does it make sense? Of course it does. Frequency observed by listener when object is moving towards the listener has to be greater. There is your final answer there, and we move on to question 6.4. How will the answer in question 6.3 change if the police car now moves away from the listener at 120 kilometers per hour? Same speed. Write down only increase, decrease, or remains the same. Let's think about it. Now it's moving away. Go back to your diagram where we talked about approaching or moving away. what do you think is going to happen now to the frequency observed by listener? If it's moving away, well done. Obviously, the frequency observed by the listener in this instance is going to decrease. It's going to be less. All right, there's a decrease in the frequency. All right, so the next part that's important is to take a look at another question. The alarm of a vehicle parked next to a straight horizontal rod goes off, emitting a sound with a wavelength of 0.34, right? Wavelength of 0.34 meters. A patrol car is moving at a constant speed on the same rod. The driver of the patrol car hears a sound with a frequency of 50 Hz, lower than the sound emitted by the alarm. Take the speed of the sound in air to be 340. Now, as you realize, sometimes we use 345 as the speed of sound, sometimes we use 340. Anything in the range of 340 and 345 the examiners can give us. But we always worry to find out from the question what they need you to use as the speed of sound in air. Question is saying, state Doppler effect in words, okay? So Doppler effect says an apparent frequency heard by listener. What happens to that apparent frequency heard by listener? We need to remember that the apparent frequency heard or observed by listener is, go back to the definition. There are two definitions. As a result of the motion between a source and an observer. All right. Write it down and always try to remember it each time you walk into an exam, because the examiner would want you to have it at your fingertips. All right. So that is 6.1, stating Doppler effects in words. That is the apparent or change in observed frequency, all right, is as a result or relative to the motion of the source and the listener. Okay. Is the patrol car driving towards or away from the parked vehicle? What do we see in this question? In this question, we are realizing that, okay, there is a lower frequency that is observed. He hears a sound with a frequency of 50 Hertz, lower than the sound emitted by the alarm. So if the frequency gets lower, what do you think? Is it moving towards or is it moving away? Think about it quickly. Frequency being lower, is it moving towards or is it moving away? Yes, you are right. If the frequency observed is lower, it means that the object is moving away. Our answer is away from the parked vehicle. Next part says calculate the frequency of the sound emitted by the alarm. Okay, so we want to find the frequency of the sound emitted by the alarm. Very simple question again, 6.3. Says calculate the frequency emitted by the alarm. What do we know? It's got a wavelength, lambda is equal to 0.34. Okay, if the frequency is 0.34, we want to find, if the wavelength is 0.34 meters, we want to find the frequency. How do we find frequency? Frequency is equal to velocity of sound over lambda. Okay? Velocity of sound in this case is 340 over 0.34. Okay? Our frequency will be equal to 1000 hertz. Just look at that. Very simple. That's understanding that particular question where the frequency is equal to 1000 hertz. Let's move on to the next question and figure out what they are going to ask us for. The next question then says, the patrol car moves a distance x meters in 10 seconds. Calculate the distance moved by the patrol car. So we've got now a situation where the patrol car is moved a distance in 10 seconds. We want to find the distance moved by the patrol car. What is it that I must find first? I must find the velocity, okay? And once I find the velocity, I can use the velocity to find the vehicle, the distance that it moves. Okay, so in this instance, I'm going to say FL 6.4 is equal to velocity. Is it going to be plus or minus? In this instance, the velocity is going to be minus at the top, okay, because it's moving away. Okay, how do we substitute that? The frequency observed by listener is 50 less, so it's going to be 950. Okay. And at the top it's V minus 0, VL. Velocity of sound is given as 340 minus VL, okay, which we are looking for, over 340 plus 0, okay, multiplied by frequency of source, which we say is 1000. All right? So, for us to calculate that simple equation, we have to find the value of VL. Our value of VL is equal to 17. Okay? The value for VL is equal to 17 meters per second. Okay. For us now to calculate the distance x traveled in 10 seconds, we know that distance x is equal to the velocity times the change in time. Okay? The velocity is 17 times change in time of 10. So the distance in this instance will be 170 meters. Okay, that is something that you can do. That is something that you can look at and carry out calculations in this regard. All right, let's move on quickly to another question. A police car moving at a constant velocity. Oh, now we got a graph. This can be represented as a graph. Interesting. Passes a stationary listener. All right. The graph below shows the changes in frequency of the sound of the siren by the listener. Okay, so the frequency is 170 here and then 130 there. What do you think this graph shows us? Okay, I think this graph is showing us a high frequency when it's moving towards the listener. All right, high frequency towards the listener and low frequency when moving away from listener. Okay, so I've got an understanding of my graph that's showing the change in frequency of the sound of the siren detected by the listener. Let's move on to the question. State Doppler effects. In words, the apparent frequency observed by listener is relative to the velocity of the source, or between the source and the listener. All right, write down the frequency of the sound detected by the listener as the police car approaches the listener. I think we have already done that in our graph, 170 as well as 130. Don't forget your units. You might lose marks for not putting units. The next part is important. It says that calculate the speed of the police car. Take the speed of sound in air to be 340. So right now we want to find the velocity. Okay. Calculate the speed of the police car, take the speed of sound in air to be 340. What are we saying here? We are saying it's moving towards, all right? When it's approaching, listener, we can consider the FL being equal to V plus VL over V minus VS multiplied by Fs. So when it's approaching, the FL value will be given by 170 in this instance, as the graph has shown us. Okay, and the velocity of sound we are given as 340. Listener is stationary. V is 340 minus Vs, which we don't know, multiplied by Fs, which we are not aware of also. Okay, and when moving away, okay, our FSL, which is 130, is equal to 340 at the top over 340 plus Vs multiplied by Fs. Now we got equation 1 and equation 2 that we can solve simultaneously. Okay, depending on the way that your teacher has taught you how to solve simultaneous equation, you need to calculate the value of the speed of the car Vs. Calculating the value of the speed car Vs will give you an amount of 45,33 meters per second. Okay, so that's your answer there for question 6.3. Let us move on quickly. Redshift of light. We have talked a bit about redshift of light. That light emitted from many stars is shifted towards the red or longer wavelength or frequency. All right, so the redshift of light is when light shifts towards the red. This concludes that the universe is expanding. All right, the stars are moving away from the earth. Here's an exemplar question. An astronomer viewing light from a distant galaxy observes the shift of the spectrum to the red end of the visible spectra. This provides evidence that the universe is expanding. Correct. Okay, now that's an idea of the electromagnetic light spectrum. That shows you the spectrum where you got red in the other end of the spectrum with a higher wavelength, and here you got the blue in a lower wavelength. So when it's in the red, it shows us a higher wavelength, lower frequency. In the blue, smaller wavelength, higher frequency. Okay, let's move on to another question. The wavelength of light emitted by a distant star appears shorter when observed from Earth. From this, we can conclude that the star is, okay, so the wavelength of light emitted by a different distance star, that's wavelength now. So we know that if the wavelength appears shorter, the frequency will be, think about it, will it be more or less? It will be more, okay? All right? If it is more, what does that tell us? It tells us that the star is moving towards the Earth. Yes, because the frequency is more, greater. And which one shows us a higher frequency? It is the blue shift. That's correct for this one. Then the spectrum produced by a moving asteroid as observed from the Earth indicates that the light has shifted towards the blue end. Blue end tells us that light is got a smaller, blue end shows us it's got a smaller wavelength and it's got a higher frequency, okay, or smaller wavelength. Okay, which one of the following frequency combinations of the observed light and the distance between the asteroid and the Earth is correct? Okay, look at the answer. Frequency of observed light, all right, it is going to be increased, right? The distance between the Earth and it is going to be decreased. So your answer here is A again. All right, so we've come to the end of this particular lesson. I hope you've learned quite a bit on Doppler effect. Go for it, go for your exams, and all the best. This is your man, Chips, who says ciao.